I'm very glad to present today's speaker, Stanisław Mrówczyński. He has a dual affiliation as a professor ordinarius at Jan Konczalowski University in Kielce, Poland. He's also a researcher at National Center of Nuclear Research in Warsaw. He got his master's degree from Warsaw University and PhD from my alma mater, Institute of Theoretical Physics in Kiev, and got his habilitation at Sultan Institute for Nuclear Studies in Warsaw in 1991. He had several postdoctoral positions, if you interpret it in today's language. One of them was in Dubna at During Institute of Nuclear Research, and another one at Regensburg University in Germany. And apparently he was the first postdoc of, sorry, I forgot.
Of Uli Heinz.
Uli Heinz, right. He was there at the time, indeed. So he got then a permanent position at Sultan Institute for Nuclear Studies, where he moved through the ranks, and he became a professor in 1999. Since 1996, he is also a professor at Jan Konczalowski University, where he, as I said, is a professor emeritus since 2005. He received several prizes for popularizing science in Poland. He got also Andrei Zoltan Prize of Nuclear Institute of Nuclear Studies in 1994. He received many prizes at the Jan Konczalowski University over the years, and he is one of the, if not the, first person who actually discovered the possibility of color instabilities in QCD back in the day, and he will be giving a talk about that today. So with that, I'll give the microphone to Stanisław.
So thank you very much for this nice introduction. So you know the title of my talk. And I would like to start with some personal remarks. So I should say that I published my first paper about instabilities over 30 years ago. And Igor just asked me how it started that I arrived to this instabilities. So when I was a PhD student, I remember I read a book about thermonuclear fusion, and I learned that the main obstacle in creating and building an efficient reactor are plasma instabilities. I remember there was such a saying that the history of plasma physics is history of discovering new and new instabilities. And since it was obvious that QCD has something to do with QED, it was rather obvious that there is a space for these instabilities, in quark-gluon plasma. And I should say that I was not the first who got the idea. So as far as I know, before this paper, there were 2 other papers where these instabilities were mentioned. But I think later on, it appeared that the observation that instabilities are possible in quark-gluon plasma was rather obvious, but the problem was to find a mode, an unstable mode, which is relevant. So it was okay, and this happened in some years later. So during the 30 years, I published about 20 papers about instabilities. 3 years ago, we published with Mike Strickland and Björn Schenke a very thick review article which summarizes the subject. But I must say many of those papers I published are rather technical, and I always wanted to have simple explanations for the problems I work with. So I decided after 30 years to prepare a whole lecture where the subject is presented only in terms of elementary physics. So arguments will be, in my talk, will be first elementary and qualitative. So let me start from the some actual title of my talk is Elementary Physics Story of Color Instabilities. And let me start from the very beginning. The very beginning is that we have hadrons, quarks, and gluons, and as you all know, we have two types of hadrons that are baryons and mesons. Baryons are built of 3 quarks which are glued by gluons, and mesons are combinations of quarks and antiquarks. And the dynamical theory which describes the structure of hadrons is quantum chromodynamics. And quantum chromodynamics has a fundamental property that quarks are confined, that quarks which carry color charges are confined in such a way that in nature there are only allowed configurations which are color neutral. And I should say that we have somewhat similar situation in electrodynamics, but in electrodynamics it is only approximate situation. We know that the structures of matter that we observe all around tend to be charge neutral. So we have atoms with the equal number of positive and negative charges. So in world of electrodynamics, we also have something like confinement. Nevertheless, if we try hard, we can separate charges positive from negative. But in chromodynamics, it seems to be a strict rule that all objects in nature must be, as a whole, must be color neutral. And then already in 70s, there appeared ideas how we can understand this phenomenon. And I would like to present the idea by Kogut and Susskind, who proposed to attribute the phenomenon of confinement to the properties of vacuum, which is treated as a material medium. And this vacuum is a very peculiar medium that electric permeability is very small or even zero. And there is a very severe consequence of this assumption that permeability is zero, because the energy density, the energy which is accumulated in electric field, is given by this elementary formula with permeability being here in denominator. Therefore, in the domains where chromoelectric field appears in vacuum, the energy density goes to infinite. Therefore, how these structures can be arranged? That if we have color charges, then the fields, the lines of electric field must be squeezed to thin strings. So, and here we have this essential difference between electrodynamics and chromodynamics. If you have charges plus and minus in electrodynamics, the lines of electric field can spread over all space. But in chromodynamics, the lines of chromoelectric field are squeezed to the string which connects the two charges. And then we can say what is the force acting between these two charges. So if we have such a configuration, we can use the Gauss law to determine the electric field. Whenever I say electric or magnetic, I always mean chromoelectric and chromomagnetic. So if you have a string with the cross section equals sigma, and then we have to compute the flux of electric field, then the electric field only goes across this disk, and then the flux is sigma multiplied by electric field. If the magnitude of the charge here is G, then we immediately get the flux, and then we get that the electric field is constant, its magnitude is constant along the string. But then it means that the potential must linearly grow with the distance between the charges. So we can say that the difference between this picture and this picture is because the property of the medium, that here electric field can propagate through whole space, and here is limited to only small domain. What is important that this linear potential can be actually studied. So at small distances, we have Coulomb potential. at larger distances, we have this linear part. And then when we study spectroscopy of heavy quarkonia, such as states like charm, anti-charm, or bottom, anti-bottom, we see a certain set of states, and then we can fix parameters of this potential. Actually, it cannot be done very accurately because the problem is that the states are somewhere here in this domain of negative energies. So actually the masses of the states are not very sensitive to this linear potential. So this procedure has limited accuracy. Nevertheless, we see that there is linear potential. And then we have very simple, such a picture of confinement. So if we have, say, meson of quark and anti-quark, and we stretch it, then it means we pump the energy to the system. And if the energy is above two masses of quarks, then the system breaks up and we have two mesons. So it is the idea of confinement. The second fundamental property of QCD is asymptotic freedom. And here it should be said that in contrast to confinement, asymptotic freedom is very well understood at present. And it is related to the problem of free normalization, the fact that loop diagrams produce infinities that we must first regularize and then renormalize, and then we introduce dimensional, usually of dimension of momentum, new parameter, the renormalization scale, but physical quantities must be free of this parameter, cannot depend. Therefore, the quantities which enter these physical quantities, like charges or propagators, depend on the scale parameter. And then one can show that, for example, strong coupling constant scales with this characteristic momentum transfer according to this famous formula, which means that when the momentum transfer is large or the distance between the interacting objects is small, then the coupling constant is small. And this is to go through carefully through this, how to obtain this formula. It is certainly not undergraduate physics. However, the very idea can be understood in terms of simple physics. So let me write sourceless Maxwell equations in a medium. So I assume that my fields of chromodynamic fields are weak enough that they can be described in terms of equations like those of electrodynamics. And then we have here fields B and H and D and E. And they are coupled by the so-called material relations. And here we have electric and magnetic permittivities. And then it is very well-known exercise to show that actually the electric and magnetic fields must obey wave equations with the phase velocity where these permittivities enter. But now it's a very important point, because according to relativity, this product of permittivities must equal 1. But if it equals 1, then it means that magnetic and electric properties of the medium cannot be independent from each other. So if it equals 1, and if vacuum, which is treated as a medium, reveals diamagnetic properties, it means that epsilon must be bigger than 1, so it behaves like a usual dielectric. So it means that charges are screened. But if the vacuum has properties of paramagnetic medium, then we deal with something that we usually don't observe in electromagnetic systems, because the dielectric constant must be smaller than unity. So it is kind of paraelectric medium, and this means that charges are anti-screened. And then it appears that in nature, there is a subtle balance usually between diamagnetic and paramagnetic properties. And it is not a priori, not usually simple to say whether a medium is diamagnetic or paramagnetic, and depending on conditions, it can be both. However, usually when we have, for example, electron gas, then electron gas of spin 1/2 particles, then electron gas typically is diamagnetic. But now we must take into account that in QCD we have not only quarks, but we have also gluons, and gluons have spin 1. And then it appears that, spin 1 particles tend to produce paramagnetic effect. And then we have subtle balance between these two, and it appears that gluons win, and vacuum is in a sense paramagnetic material. And then electric properties are such that charges are anti-screened. I found information that actually Tuft got this idea, and then it was nicely developed in this paper from American Journal of Physics. And what is very interesting, that this is not only illustration, but actually one can even get quantitatively correct formula of asymptotic freedom in this way, computing magnetic properties of vacuum. Okay, so we have hadrons and with confined quarks, and now there is a problem how to produce a quark-gluon plasma. And we have essentially two technologies. One technology is simply squeeze nuclear matter. When we have a system of nucleons and we try to squeeze it, this because of conservation of baryon charge, these baryons cannot disappear. And when we squeeze them, and if we take into account that baryons are of finite size of the order of 1 Fermi, this is evident that above certain density, baryons must overlap. And then it doesn't make much sense to talk about baryons. And then the right degrees of freedom are quarks. And this is the technology that is realized in nature in neutron stars. We have gravity, which squeezes baryonic matter, and then it is expected that in course of neutron stars, we have indeed quark matter. And there is the second technology, which is simply heating even the vacuum. Because when we heat, the point we provide heat, then the point is that number of hadrons is not conserved. And if we have hadrons which don't carry conserved quantum numbers, their density simply grows like number of photons with temperature. If we neglect the mass, or if the mass is much smaller than the temperature, then the density of hadrons grows, and then we essentially return to the first picture, that if the density of hadrons is too high, then hadrons overlap, and then we deal with quark-gluon matter. So for me, it is absolutely evident that quark-gluon plasma exists, and essentially everything which we need to have it, to expect that quark-gluon plasma exists in nature, is the very fact that hadrons are of finite size. Okay, now let me move to the phase diagram of strongly interacting matter. So here we have temperature, and here we have baryon density. And I start from 0 temperature and from 0 baryon density. What we exactly know, we know that at 0 temperature and at this density of baryon charge, we have normal nuclei. And then we know that nearby we have also nuclear matter, but when we heat up this matter, when the temperature grows, then because of finite size of hadrons, we have a new phase of matter, which is quark-gluon plasma. We also expect to have color superconductor here because at sufficiently high charge, baryon charge density, we expect that there is a formation of Cooper pairs. We also, when we produce quark-gluon plasma in relativistic heavy ion collisions, then in the center, in the mid-rapidity domain, we have almost no baryons, and then you have baryon-free matter, and then there are quite strong arguments that here it is a continuous phase transition, which is like of crossover, but at finite baryon density, we expect to have first-order phase transition. But having these two information together, we know that there must be a point where that something has changed from crossover to first order. So we expect to have critical point, and there are some hard efforts to find this critical point. But I should say that actually this phase diagram is not very complicated, and I produced a diagram of water, but usually diagram of water is presented in different way, but I tried to make it in analogous variables. So here is temperature, and here we have density of molecules. And as you see, this diagram is pretty complicated, and it looks more complicated than this one. And this is complicated, even so I cut off this domain of small temperatures, because here we have several complicated quantum phases, different types of ice. So water provides such a complex diagram. So I think that this diagram is highly simplified. Presumably we will find that nature is more complex. And we believe that quark-gluon plasma is produced in collisions of relativistic heavy ions. So we have two ions, we collide them, and we collide them in such a way that there is a big overlap. And then we produced remnants of these two nuclei, go backward or forward. And then in between, we produce a very hot zone. And here we have quark-gluon plasma, which evolves, and then finally we observe hadrons. And this can be also presented in such a Minkowski space diagram. We have two nuclei which fly with almost speed of light. At t equals 0 and z equals 0, they collide. And then what is important that we expect to have a boost invariant picture. And then everything depends not on time, but on tau, which is the combination of time and z variable. And now there are good reasons to believe that this picture is not right in the whole domain of rapidities, but in central domain is approximately correct. And so here we produce quarks and gluons, which are produced at the first moment, and then they are, what is very important, out of equilibrium. But there are secondary collisions, the system equilibrates, so then we have equilibrated quark-gluon plasma, and then when the temperature drops, so we have a phase transition to hadrons, so we have hadronization, and finally the system is so dilute that the mean free path of hadrons becomes longer than the size of a system, and the system decays into free hadrons which fly to our detectors. And in my story, I will be interested only in this short domain at the very beginning, when the system is in pre-equilibrium state. And now let me compare quark-gluon plasma to electromagnetic plasma, because there are some similarities and there are some differences. So underlying microscopic theories QCD here and QED here. In QED, we have only one type of interaction, that is charges are coupled to photons. Here we have this type of coupling of quarks or antiquarks to gluons, but we have also self-coupling of gluons, and we have 3-gluon coupling and 4-gluon. So we have fermions and bosons, so quarks, antiquarks, and gluons. There is similar situation in electromagnetic plasma. We have electromagnetic plasma is weak coupling in this sense that the weak coupling, that coupling constant is small, while in QCD the coupling constant varies between, say, 0.1 and 1. So it is also very important difference. There is also one difference which to my mind is not fully appreciated in our community. For properties of electromagnetic plasma, it is very important that we have massive ions. And because ions are much heavier than electrons, there is factor of 2000 at least, then we have very inefficient transport of energy from electrons to ions. And this means that electrons and ions can be treated for relatively long time as two independent fluids of different temperature, of different velocity. And we don't have analogous situation in quark-gluon plasma, because quarks and antiquarks and gluons are almost massless. Therefore, we don't have such a situation. So there were produced many papers where magnetohydrodynamics of QCD was discussed. But in my opinion, this magnetohydrodynamics of QCD is very different from QED because of absence of ions. So this is the subject for separate story. I will not continue this. Now we have a huge simplification in our considerations that quarks and gluons, which are our plasma constituents, are almost massless. And then the temperature, as long as we consider plasma which is in thermodynamical equilibrium, then T is the only dimensional parameter, and we can express all quantities through this parameter, that is temperature. So density of partons is T cube. Interparticle spacing with 1/T. Energy density is like in Stefan Boltzmann law, so it is T to the 4th power. And then pressure is of the same power. And throughout my whole seminar, I will make a very important assumption that plasma from the earliest stage of relativistic heavy ion collisions is weakly coupled. So I assume that at this short period, right after the collision, we are in the regime of asymptotic freedom. And there is one very simple argument, the dimensional argument, that if we deal with the many-body system, then Q should be replaced by analogous quantity, but which characterizes the whole system, and it is energy density. And energy density is the largest at the earliest stage. And if you even try to do it in a more quantitative way, you arrive that this energy density, but energy density of whole energy, not only energy which is thermalized, but the whole energy in this pre-equilibrium phase. And so at the collisions which are studied right now at LHC, this parameter is of the order of GeV. And then it is quite reasonable to my mind to assume that we are in the asymptotic freedom regime, and then that we can describe the whole system in terms of perturbative QCD. And now let me discuss some properties of the plasma system. So the fundamental property that I will also return in a moment is the effect of screening. So if we have one charge, say charge positive here, then the negative charges from the medium tend to approach it to neutralize it. Therefore, if we have a charge, then the charge is neutralized at the length, which is called screening length. And I will explain in a moment, it is of the order of inverse GT. But I would like to show that because of this property, weakly coupled plasma is with a medium which reveals strongly collective behavior. And why it happens? So if we have a radius screening length with this of order 1 over GT, it is inverse Debye mass, which is the screening mass, then we can introduce the concept of Debye sphere. Debye sphere is the sphere of the radius of screening. And then if we compute the volume of this Debye ball, you get simple formula. Then the density of quarks and gluons is roughly 2 to cube. And then when we compute the number of partons in this volume within the Debye sphere, it is 1 over g cube. And then we see that this is much bigger than unity if g is smaller than 1.
Stanisław,
So, yeah?
There is a question from Masoud. He's asking, to what stage can we assume that the plasma is weakly coupled? I think at what stage?
So I assume that it is in a pre-equilibrium phase, which lasts fraction of a Fermi. But this is really a quantitative issue to compute it. Actually, I tried to make some phenomenology. So I think at the very early, just right after collision, the characteristic scale is indeed bigger than lambda QCD, but later on, it is no longer the case. So I suppose that at the beginning, we have weakly coupled system, which later on becomes strongly coupled. So my first remark is that if plasma is weakly coupled, then it behaves in a very collective way, because what does it mean? It means that in the range of electric forces, there are many charges. So their behavior must be collective. And now let me explain how one gets, using these very elementary arguments, that the Debye mass is GT or ET. When I talk about electromagnetic system, I usually say E. When I talk about quark-gluon plasma, I say G. So let's try to first explain why it happens that we have exponential decay of a potential and why the Debye mass is of this order. So this can be very easily obtained. So we refer to the Poisson equation, which determines behavior of a potential. So we have Laplacian of the potential, and on the left-hand side, we have minus charge density. But what is important? Imagine we put a charge in our system, but if we put a charge, say positive, then negative charges tend to approach this, because it is then more energetically favorable. But how it is favorable? It is controlled by the Boltzmann factor, because EV is potential energy. So if the temperature is very high, it doesn't much matter. But if the temperature is low, then it matters much more. So it is the formula which can be easily guessed. So we should solve Poisson equation with such a charge density. And now to make the problem simple, let's assume that the potential energy is much smaller than the temperature. So we work in the high temperature domain. And if it is the case, then we can expand this exponent, And then we get this approximate expression. We plug in this expression into Poisson equation. And so we have V on the left and on the right. So if we consider one-dimensional problem, so we have such an equation, and then it is completely evident that we must have exponential decay. And then, simply from this factor here, we get the expression for the biomass. So the biomass, and it is what is usually used in plasma physics, it is E multiplied by the density of electrons divided by temperature. But we don't have density of electrons, but we have density of partons, which is proportional to T cube. So we replace this with T cube, and then we got here ET. So it was elementary physics explanation of this formula that I will use repeatedly later on. Okay, and what is the mechanism there is a very important phenomenon which is called plasma oscillations. So imagine you have charges positive and negative. They are more or less homogeneously distributed. But because of fluctuation, we have a surplus of negative charges here, and we have positive charges here. And then it appears that if we have such a situation, then electric fields show up. If electric field shows up, the charges start to move. And then we have this such a wave of electric field, and there is characteristic frequency, which is called plasma of Langmuir frequency. And again, how in terms of elementary physics, we can get this behavior. So imagine you have negative charges and positive charges, and you slightly displace them with respect to each other. So you displace them by x. Then you compute electric field. So you assume that here is the surface, such a cross section of this is S, surface of this. So you easily compute the charge which is here. So you have flux, you have charge, and then you find what is the electric field here. And then you can solve equation of motion when you have here mass, force, and charge. And then putting all these formulas here, you get the equation for harmonic oscillator with this frequency. So this is the situation which, strictly speaking, corresponds to the infinite wavelength or infinite wavelength. But it clearly shows that you have this oscillatory behavior. And these arguments can be translated into Quark-gluon plasma, where you replace E by G. T, density of charges is not fixed, but equals T cube. Mass is T because it's characteristic energy. And then you find that the characteristic frequency of plasma oscillations is GT. And now Landau discovered very beautiful phenomenon which is responsible for damping plasma oscillations. So imagine you have a wave of electric field, and you have such a electric field, and there is a phase velocity of this wave, which is frequency divided by wave vector. And now imagine that you have an electron which moves with the velocity which exactly equals phase velocity. If you have such a situation, then such an electron does not feel this as a wave, but as a constant electric field. And then depending on the phase, whether the electron is here or here, the electron is either accelerated by the wave or decelerated. It means that either the energy is transferred from electrons to wave or from wave to electrons. But it appears that sometimes we can have amplification of waves, and sometimes you can have a damping of waves. And in this way, I arrive to the central topic of my story, that are instabilities. What are instabilities? So imagine you have a stationary state, and this is a certain physical quantity. And then there is a small fluctuation. And the system is stable if this fluctuation with time passing decays, and the system returns to this initial state. And we deal with instability if the initial fluctuation exponentially grows. And it appears that in plasma, we have many instabilities. And then instabilities are split into two categories. If we have instabilities in configuration space, they are called hydrodynamic instabilities. And instabilities in momentum space are kinetic instabilities. These hydrodynamic instabilities are usually related to the behavior of the plasma system at the border, what happens at the edge of the plasma. And this is the domain of non-perturbative domain of QCD. So I don't think that here this analogies with electromagnetic plasma can be used. But in the domain of kinetic instabilities, I think that we can learn a lot from electromagnetic plasma. And kinetic instabilities simply occur because the momentum distribution is different from the equilibrium distribution. And then kinetic instabilities can be split as all collective modes into longitudinal and transverse. Longitudinal modes are such that the wave vector is parallel to the electric field. And transverse are such that the wave vector is transverse to the electric field. And then using Maxwell equations, we immediately find that if K is parallel to E, then there is charge involved in this phenomenon. This is the Gauss law tells us this. But if K is transverse, there are no charges, but there are currents. And now the crucial question of my whole story, which are modes, which modes are relevant for QGP? These are longitudinal and transverse. And typical situation which was discovered as a first in electromagnetic plasma are longitudinal instabilities. And typical situation when they occur is that we have a system of plasma and, for example, we want to deliver some energy to the plasma and we orient to the plasma system a beam. Then beam interacts with the plasma and provides energy. And then momentum distribution of such a system is schematically shown here. So we have distribution, momentum distribution of system of particles, which include plasma and a beam. And here, this part is a distribution of plasma particles. And we add to this system a beam of given momentum. So the total distribution looks like this. And then it appears that this little piece of the distribution, when the number of particles grows with velocity, that this little piece is responsible for instabilities. This is this piece when the energy is transferred from particles to fields. And how it goes. As I explained to you, it is exactly this phenomenon which is related to Landau damping. So we have a wave, and this is phase velocity of the wave, omega over kx. And now we have particles which can be slightly faster or slightly slower. But we have also distribution of particles. So we can say we have more particles that are slower than the phase velocity of the wave than particles which are faster. And then it is such a nice elementary exercise when you try to think what happens to particles which are slightly faster than phase velocity. They feel this constant electric field, but they feel it only for a shorter time than those which are here. So one should think for a moment about this problem here, but the net result is that if we have momentum distribution of this shape, that the number of particles decreases with the velocity of particles, the net result is that the energy is transferred from wave to particles. And this is responsible for Landau damping. But if we have opposite configuration, then the net result is that the energy is transferred from particles to fields. Therefore, if you have momentum distribution like this, such a configuration is unstable. Therefore, whenever we have such a non-monotonic momentum distribution, then we have a guarantee that such a system is unstable. However, in heavy ions, we don't expect to have something like this. Therefore, longitudinal modes are not relevant for quark-gluon plasma from relativistic heavy ions. However, it appears sufficient for some type of instabilities is that momentum distribution is anisotropic. So what are general features of such a momentum distribution of partons from relativistic heavy ion collisions? So momentum distribution has single maximum and it monotonously decreases in all directions. So longitudinal modes are irrelevant. However, there are unstable transverse modes. And what is the actual situation in such a collision? When we have initially collision, and if we took into account all partons which are produced and also those partons which are remnants of incoming nuclei, we can say that the momentum distribution is elongated along the beam. So using the language, the terminology from nuclear physics, it is prolate shape. But after some time, these valence partons escape from such a box where we measure momentum distribution, and the distribution becomes oblate. So it means that on average, longitudinal momentum is smaller than transverse momentum. And then it was shown in numerous simulations that such a configuration, while this configuration is transient and disappears after a very short time, such a configuration survives for relatively long time. And what happens if you have such a situation? So if we have such a situation, on average, our system is color neutral. Our system is color neutral. It means that for current, so charge density and charge current, our average is 0. However, when we compute the correlation function, it appears that the correlation function is non-zero. And there is a simple exercise is to consider the simplest possible correlation. So we consider particles which are free, and there is only one type of correlations. We say point x1 is correlated to point x2 if it happens that there is a particle that can fly from this space-time point to this space-time point. If there is such a particle in our system, then these 2 points are correlated and the currents are correlated as well. And this is this formula which says that this tells me whether these points can be connected by a particle with velocity v. Then we have a particle distribution, and then we take the integral over it. And then when we make this simple exercise, it appears that there is kind of kinematic property of the system, that the system tends to split into current filaments. So how it happens? So if we have here, in this direction, the system is elongated. So this is, in heavy ions, this is transverse direction and this is longitudinal. But we have surplus of momentum in this direction. So if it happens that there are, say, 2 partons flying in this direction and they have the same charge and they generate current, the system is on average neutral. So there must be another current which is compensating this. And then one can say that when the system is not isotropic, but anisotropic, then the system has a natural tendency to split into current filaments, and the filaments of these currents are directed along the direction of the momentum surplus. But this is only kinematics, but what happens dynamically? And here dynamics must be considered. So let me consider such a filaments, and current flows in this direction here, in this direction here, and so on. So the current is shown here, but we have also magnetic field because we have Ampere law. So Ampere law tells us that once we have current, we must magnetic field. But magnetic field is shifted. So maxima of the magnetic current appear here at this borderlines of the filaments. And now it is a simple exercise to consider what happens with particles which form the current, because there is a Lorentz force which acts on these charges. So let's consider this charge here. If it flies in this direction, it positively contributes to the current of this filament. You compute the Lorentz force and you see that the Lorentz force tries to bend its trajectory in such a way that this is moved to the center of the filament. But if it flies in this direction, the Lorentz force acts here, and then this particle is transferred to the neighboring filament, where flying in this direction again positively it contributes to the current. So the magnetic field sorts out particles in such a way that they positively contribute to the currents and the current grows. So it is the dynamical reason for the mechanism of filamentation. However, we have this mean field mechanism, which is responsible for growth of the field, but we have also scattering in the system. It is kind of dissipation. So the instability can grow only if it is faster than the dissipative process. So part-on-part scattering provides dissipation, and we must consider two types of scattering. This is hard scattering. It is scattering when the momentum transfer is of characteristic, I use T like temperature, which is the characteristic momentum scale of the system. So, and in equilibrium plasma, it is simply temperature. So we have hard scattering if the momentum transfer is T, and you have soft scattering if it is GT. And then it appears that hard interactions are not very frequent, but soft are frequent and this changes to orders of 2 powers of coupling constant. However, what is very important, instability is a mean field effect, and its characteristic frequency goes like GT, while even the soft collisions go like G square log T. So if G square is much smaller than unity, we can say the frequency of hard collisions is much smaller than that of soft collisions, and is much smaller than that of collective phenomena. So what does it mean? It means that collective phenomena, mean field phenomena in weakly coupled plasma are the fastest. Therefore, for this reason, the weakly coupled plasma is unstable. And these were only such a qualitative arguments, but then there were simulations performed by my colleagues already in 2005, and they considered such a system in 1+1 dimension and only SU2 group. And then they started with such a configuration that they have partons, and they have only fields at the level of noise. And then they observed, they computed the energy which is accumulated in fields. And then they observed that with time passing, first nothing has happened, and suddenly this energy which is accumulated in fields started to exponentially grow. And what was very important, the system was of course anisotropic and strongly anisotropic, and the growth rate here of this energy accumulated in fields exactly coincide with this frequency, imaginary frequency of the maximally of this fastest mode which was found analytically. So it was found in numerical simulation that in the simulation the growth of the fastest growth was observed. And then what is the role of these instabilities? So the most important is that instabilities speed up the process of equilibration of quark-gluon plasma. And how it happens? It happens mostly because the instabilities help to isotropize the system. Because when you have such a system, and here we have surplus of momentum in this direction, you would like to isotropize the system. And then parton-parton scattering the cross-section is very similar to the famous Rutherford cross-section. And we know that Rutherford cross-section is strongly peaked forward and backward. For this reason, Rutherford cross-section is not very good for redistributing momentum. But it appears that when you take into account this collective effect, that there is a magnetic field and Lorentz force, then you see that the magnetic force acts just in transverse direction to the momentum surplus. So the change of momentum is exactly what we really need for isotropization. So this is one reason. The second reason, and this was again observed in nice simulation, that people started with strongly anisotropic system, and then they computed elements of energy momentum tensor. And they observed that this energy momentum tensor, which initially was very small, was exponentially growing, and the system was evolving towards isotropy. There's also another reason, is that when we think about such a system that is strongly anisotropic, then we see that also here are fields. And when we have fields, we have pointing vector, because we have transport of these fields. So we have momentum of fields. And then we also see that momentum of fields is also in the direction which is transverse to the direction where we have momentum surplus. So again, fields also help to isotropize the system. So this is the reason why systems which are unstable relatively can reach equilibrium, thermodynamic equilibrium fast. But there are also another interesting features. So there are very specific transport properties of unstable plasma. So if we consider such a system, we can consider the most important for this configuration is the mode which is the fastest. So the fastest mode is this one with this mode of filamentation. So here I have drawn what is the orientation of electric field and current, magnetic field. And then when we consider what happens to a test particle which enters such a system. So it can enter in this direction or in this direction. And here it was very hard technical work. And we computed energy loss or in such a system. So we have plasma in unstable configuration and we have a test particle. And then it appears that there can be very interesting phenomena which can occur, because we can have energy loss, but we can have also energy gain. It was very funny because we found this energy gain, and then I was convinced that we have done something wrong, that we have sign problem. And then I looked through literature, and then I found that there are even considered plasma accelerators. we can cook up such a configuration of plasma that it acts as an accelerator. And then we found in our computation that indeed, depending on our initial conditions, we can have exponential growth of the energy of particle or exponential decrease of the energy. What is also very important that this initial, the characteristic energy change is order of magnitude bigger than in equilibrium plasma, because this characteristic value, which is considered here, is only 0.1 in equilibrium plasma of the same density. This is also what is important. This behavior is very directionally dependent. Then we computed something that are for radiative energy loss, the quantity which is called momentum broadening is crucial, because for radiative energy loss, we need to multiply this momentum broadening by probability to emit a gluon. So Q hat determines radiative energy loss. And first it was found in numerical simulations that we can have exponential growth of Q hat. And then we have made fully analytic calculations, which also shows this. And again, these quantities here of Q hat are much bigger than in equilibrium plasma of the same density. We have exponential growth and very large numerical value. Okay, so I feel I talked too long, so let me conclude my story. So first I would like to stress that non-equilibrium quark-gluon plasma is unstable. And the instability is generated by transverse modes. And these are modes which are relevant for relativistic heavy ion collisions. Instabilities are responsible for fast equilibration of the system. And at the end, I only mentioned that unstable quark-gluon plasma is a highly opaque and anisotropic medium. Okay, that's all. Thank you.
Okay, thank you very much for a nice presentation. Now we will have some time for questions. So right now, Masood Chokri has 2 questions.
Hi, thanks for the nice presentation. I wanted to ask 2 questions, and one is that how can we understand the equilibration of quark-gluon plasma using weakly coupled theories?
Okay, so as I tried to say, so if you have weakly coupled plasma, then it is very hard to understand how it is possible that it equilibrates fast. So, because as I said, because parton-parton scattering is very strongly forward-backward peaked. So these collisions are not very efficient in transporting a momentum. And then it is what is done in a collective manner by instabilities. That instabilities help to isotropize the system. Instabilities, we can say, we have initially an isotropic system, and instabilities push the system towards isotropy. So it is their role. So what is difficult for particle-particle collisions is much easier to achieve in this collective mechanism.
Thanks. My second question was about your comment on MHD of QCD. I don't know if you have a time to explain it much further. You said that it is different from the MHD of QED.
Yes, I think the essential difference results from huge ratio of masses of ions and electrons. Because if you have ions and electrons, and if you have, say, hot electrons, it is a very inefficient process to transport energy from electrons to ions. For this reason, you can have such a situation, and it is observed in plasma, that you have hot electron field and cold ions, that it takes time. So the time for equilibration is long. Or you can have something different. For example, typical situation in electron-ion plasma is that the system equilibrates and neutralizes very fast. That is, charge density is everywhere zero, nevertheless, there are currents, and currents can exist very long, and you have many interesting phenomena like dynamo effect. So you have long-lasting currents, and it happens just because of inefficient transport between electrons and ions. And here we don't have such a situation because charges of both sides, of both signs, so plus and minus, are of the same mass. So quark-gluon plasma could be similar to the plasma of electrons and positrons, and not electrons and ions. And magnetohydrodynamics, which is usually described in textbooks, it is the magnetohydrodynamics of electrons and ions. So it is, in my opinion, it is very different system.
Thanks.
Okay, I think we have another question. Zoran, would you like to ask yourself, or should I read your question? Okay, do you have, so this is a question from Zoran Schlichting. Do you have a suggestion for a unique signature of plasma instabilities in the QGP other than isotropization, which can also occur kinetically on conceivable timescales? I guess that is, for instance, the production of electromagnetic probes could have interesting properties. Has that been calculated?
Yes, so I think that, for example, this picture, when we consider jet quenching, all jet quenching experiments measure jet quenching for jets which are produced exactly perpendicular to the beam. And for example, if I treat this picture seriously, I see that Q hat rapidly decreases when I change the angle. So I would be interested in such jets which are deflected. That jets, say, in one has somewhat forward rapidity and backward jet has somewhat forward rapidity. And such a deflected jet, it would correspond to the different angle with respect to the anisotropy angle. So I would expect that there can be significantly different quenching depending on the angle. And if whole energy loss comes from the plasma which is in equilibrium, it doesn't matter, should be exactly the same. But I believe that because of very high density and because of very large Q hat at the beginning, because of very large energy density, I believe that substantial contribution to jet quenching comes from this early phase. And this early phase is very directionally dependent. So this would be one option. There are also some other, for example, I think that if we manage to measure energy loss fluctuations, this picture also suggests that there should be very large energy loss fluctuations, much larger than in equilibrium medium.
Okay, thanks. I don't see questions from the audience, but I did have a question of my own. You were talking about the longitudinal transverse instabilities, and one of semi-conclusions you said that there shouldn't be any longitudinal contributions. I kind of want to disagree with that. When we do have jets flying through the plasma, they naturally produce what you describe as the interaction with the stream or whatever instability you call it in plasma. So that's your classical example of longitudinal instability.
Yes, of course. But then if we have a macroscopic beam of particles, then of course, then we have exactly such a situation like in electromagnetic plasma, and then there is open space for instabilities.
Jet is producing something like that.
Huh?
Jet would be producing
but initially we start with only single parton, and this number of particles grows because of secondary interactions. So we have many particles in a jet after longer evolution, and I am interested only in this very early period. Of course, there is such a possibility, but to my mind, this treatment is then not legitimate.
Okay, okay, fair enough.
I can comment a little bit that Christina and myself looked into this years ago, just trying to inject jets, and the time scale for the instability was just too long physically, right?
Yeah. Because
if the density difference was not too high.
Yeah, I agree fully with Mike. If the density of particles in a jet is not high enough, then the time scales are long.
Okay. There is any other questions from others, because I don't want to steal the show, but I do have another quick question. When you were talking about the role of these instabilities for the isotropization, that's kind of relatively clear in a way. It kind of washes away the anisotropy, strong anisotropy that you started with, and it kind of washes it away. So it's kind of natural progression. But what about thermalization? It seems like it doesn't help much to the actual thermalization, does it?
Yes. Yeah, I think that it only helps to redistribute momenta, but it is not able to form this exponential distribution for this we need a genuine dissipation, because it is, here is very fundamental argument, because it is mean field dynamics.
Right.
So mean field dynamics cannot, so it is very, as you know, Landau damping is a very peculiar process. It is mean field dissipative process. So I think that, but it is very important because it is the isotropization is most difficult for particle-particle scattering.
Okay. Any other questions? Okay, Mike, go ahead.
Well, I have a comment on that. So at least in the expanding case with the non-abelian instability, also in the non-expanding case, what you see is this turbulent cascade once the soft sector gets over-occupied. And that kind of sets the stage for the later thermalization in some sense, because it seeds, it kind of fills the valley between the hard particles and the soft sector.
Yeah.
But that will be something sort of like longitudinal instability, kind of, isn't it?
No, this would be the normal Weibull transverse magnetic primarily. There's also longitudinal modes coming from the commutators, but they're secondary instability.
I see. Well, any other questions before I shoot another one of mine? So you mentioned about this kind of difference between QED with the ions and QCD plasma. Well, it seems like a natural place for developing those instabilities will be in hard, in dense quark matter with the UND quarks. There will be always electrons necessary because of the beta equilibrium. And as a result, you might have something similar when you have a two-fluid component with the quarks giving you one component and the electrons another one. Isn't it right?
Yes.
And in that case, are there any instabilities of the sorts that you were discussing, or maybe others that might be relevant for neutron stars? Quark stars, I should probably say.
So I should say that this electromagnetic analog, this Weibull instability, was experimentally observed in plasma experiments with lasers.
But not in quark matter. I'm asking about quark matter in neutron stars.
No. I don't know. I don't know whether it is relevant.
Okay, sounds good. If there are no more questions, we will be wrapping this up. So I would like to use the opportunity to thank Stanisław for a nice presentation, for taking time explaining all this at such elementary level that everybody can understand. So thank you.
Thank you very much.